Hi, I just want to give you a couple hints on the center of mass WebAssign. When we have a situation where a solid is irregular, it's easiest to split it into pieces and then consider each piece as existing only at its center of mass. So when I look at this shape, I see a chunk of mass 2m with its center of mass located here. I see a chunk of mass m with the center of mass located here, and a chunk of mass 3m with the center of mass located there. And then I would use the center of mass equation and plug in those coordinates for those three pieces. Number 2 is similar to the problem we looked at in class. B is a little strange. In B, it's asking if the man moves a certain distance, how far is he then from the woman? Well, for everybody, the man is heavier than the woman, so the woman moves more than the man. And how it ends up working out to keep the center of mass stationary is the product of how much the man weighs times his distance he goes is equal to the mass of the woman times how far she goes. So from that, you can figure out how far the woman slides, how far apart they were to start, and so you can figure out how far apart they end up. 3 is tricky because we're dealing with a volume problem, really. If this block has a mass of m, and then we double each of its 3 dimensions, then the second block doesn't have a mass of 2m. It has a mass of 2 times 2 times 2 is 8m. And so if we're measuring from the outer edge of the small cube, then the center of the first cube is at 1/2 L naught. The center of the second cube is 1/2 L naught from the left edge. And then when you go to the third cube, you would go 1, 2, 3, and then another 1.5. The mass of this one, well, it's 3 times as big on all 3 sides. So 3 times 3 times 3. In number 4, you have velocity components instead of position coordinates, but you'll use the equation the same way. You just use the velocities instead of the positions. I went over this, I think, in set 1, but not yet with set 4. So it's not hard to get the answers, but I'll go over it next time I see you. Number 5 is not so bad. I bet you can figure that one out. 6 and 7 get back into kinematics, where you're going to use kinematic equations and then apply your understanding of center of mass to them. And number 7, as we talked about in class, the center of mass continues to move in a parabola even though the pieces don't. So the center of mass essentially lands where the object would have landed if it hadn't exploded. So if the center of mass lands here, that means that the 2 equal mass pieces have to be equidistant on either side of it. 8, 9, and 10 are tricky. For set 1, we did number 8 in class and number 9 in class. And so you should definitely try number 10. For set 4, I will go over these with you next time I see you. Give it a shot. Basically, you draw a picture, you define a zeroed coordinate, then you draw a new picture for time 2 with the center of mass in the same location, and then solve for whatever it is that you're looking for. They're annoying. They're kind of complicated, so if you have a hard time with them, I definitely will spend time on them with you next time I see you.